What's up, everybody? It's your boy, Coach Shipley, coming to you live from the 865 with a little math for you. Okay, I can't do that the whole time, so let's just talk normal to you now. So we're going to talk about some rotational symmetry. All right, so right here is the definition for rotational symmetry. There we go. All right, the figure can be turned 180 degrees or less, okay? So 190, whatever, something less than 180, and it looks exactly the same as it did originally, then it has what we call rotational symmetry, okay? So down here, let's look and see if some of these have rotational symmetry. All right, that's going to be a little bit easier for me because I can just rotate it right here. So the question is, can I rotate this less than 180 degrees and get the exact same shape I started with? So let's do it. So 180, just so you know, would be where this point is all the way down here, right? That would be 180 degrees. 360, of course, would be if I rotate it all the way around. The point was back at the top again. So it's got to be less than 180 or 180. And we see as I start to turn this right about there, we get the same shape we had originally. So this star does have rotational symmetry. I can rotate it less than 180 degrees and get the same shape that I began with. All right. And now let's look at this shape. This is called a trapezoid. Okay, it's a four-sided shape that has two lines that are parallel, the top and bottom ones. So let's see if we rotate this one. Can we rotate it 180 degrees or less and get the same shape we started with? Okay, ignore the two up there. So it's still not the same way it was before. Okay, that's not the same. If we keep going, that's 180 right there. So that's not the same either because the top line is bigger than it was and the bottom line's smaller, okay, because the small line was up top like that. So we wouldn't get the same shape until we went all the way around 360 degrees. So it has to be 180 or less. So this one does not have rotational symmetry. So for the star we could put yes, and for the trapezoid we could say a resounding no. All right, now let's look at this triangle right here. Can we rotate it less than 180 degrees and get the same shape? Well, let's try. So we rotate it, and oh, looks like right there we get the same triangle that we had before. Okay, so this one does also have rotational symmetry. Come on, marker. There we go. So yes, the star or the triangle also has rotational symmetry. All right, so I'm gonna go ahead and pause it real quick and let you guys try to determine if you think 4, 5, 6, and 7 have rotational symmetry or not. Okay, so number 4 right here, this triangle, it does not have rotational symmetry. I don't get the same shape again until I get it all the way back around to where it started. So that one does not. The letter S, it does have rotational symmetry. Okay, I can rotate it 180 degrees and I get an S again. So the letter S does have rotational symmetry, but the letter B does not. 180 degrees gets me to a backwards B, and nowhere in between do I get a B, so it does not have rotational symmetry. And then SOS, strangely enough, even though it's 3 letters, does have rotational symmetry because at 180 degrees it's SOS again. Alright, so it's got to be 180 or less. And that one does it at 180, so yes, it does have rotational symmetry. Let's keep on cruising. Okay, so which of the following here have rotational symmetry and why? So one cool thing that's on here is I've got 2 underneath, so you can kind of see it. If I start right here, if I start to rotate it, this does have rotational symmetry because you can tell right here it covers up the original again, right? So this one you can see does have rotational symmetry. Whoa, messed that up real good, didn't I? But you still know the answer. What about this one? Does it have rotational symmetry? So let's see if we can rotate it 180 and get the same shape. Oh yeah, awesome. So we do that 180 and we get the same shape we had originally. So we could say yes for this one as well. It does have rotational symmetry. What about this little guy? So let's try to rotate him. I don't know why it's a him. Why can't it be a her, right? That's almost sexist. So if I could select it here, maybe we can rotate it. It's not wanting me to. Anyways, sorry, you can tell by looking at this one's not going to have rotational symmetry because this side is longer than this one. So when I rotate it 180, it's not going to be the same because it's going to be a shorter side over here than this one. So that one, we could say no, it will not have any rotational symmetry. Ooh, that's a pretty O. So that one's not going to. Okay, so now let's talk a little bit about specific shapes that have rotational symmetry called regular polygons. Okay, so we're talking about, again, rotating an image to where it's on itself again. So this square right here, it has rotational symmetry. Okay, we can rotate it and get a square again, right? But what we want to look at is how many degrees does it take? Or what's the fewest number of degrees to get the original shape again? So the way to determine this, when you have what's called a regular polygon is any shape where all the sides, okay, are the same length. So like a square, a triangle, a pentagon, a hexagon. Okay, so some of those might be new words for you, but we'll look at some of them and you can tell what I'm talking about maybe whenever I show you some more examples. So the way you determine, though, the whole question is, what's the fewest number of degrees it will take to get this shape to rotate and be the same shape we had originally again? What's the fewest we can have? So to figure this out, all you need to do is do 360 divided by, okay, the number of sides of the regular polygon. So for a square, we would say 360 divided by 4, because a square has 1, 2, 3, 4 sides. 360 divided by 4 is 90. So we know it's going to be 90 degrees. It's going to take a 90-degree rotation to rotate this square onto itself. So and you can tell if I go from the top and I go to the right. All right, so I went from here to here. That is a 90-degree rotation, and now it's a square again. Anywhere in between, it didn't really give us the same shape we had originally because the lines are going diagonally and stuff. But right here, it's exactly the same position as it was in before. We just rotated it onto itself. Okay, so let's look down here at a couple of these. So right here, this is an octagon, right? Like a stop sign shape. It's got 8 sides. So for it, we would do 360, and you would divide that by 8, okay, since we have 8 sides, and that's going to give you 45 degrees. Okay, so 45 degrees is how many degrees it would take to rotate an octagon in order to put it on itself. So just not even a quarter of a turn. Okay, that's just 45 degrees. We're not going from the top all the way to a side to get 90. We get one in between there, halfway to 90, which is 45. Okay, so yeah, that's a situation where it's not going to be as far because you've got more sides. All right, and then this shape right here, this isn't really a regular polygon because the sides are all different lengths, but you could rotate it 180 degrees and get the same shape again. So this one does have rotational symmetry, but we couldn't use it to divide by 4 sides because it's not a regular polygon. Okay, a regular polygon, the sides all got to have the same length. Right, so 360 divided by 4 would be 90, so we'd expect 90 degrees, but 90 degrees doesn't give us the same shape again because it's not a regular polygon. Okay, it's like a diamond shape or parallelogram kind of thing. So it's got to be a regular polygon in order to be able to do this rule to determine how many degrees it takes. Okay, so I want you guys to go ahead and try these. Okay, these are all regular polygons. Okay, I'm going to pause it and you guys figure out what the smallest number of degrees it would take to rotate the shapes onto itself. Okay, it says a triangle, but whatever the shape is, see how many degrees it would take to rotate onto itself. All right, so go ahead and do it. No, really, pause the video. Pause the video and do it yourself. Practice makes perfect, ladies and gentlemen. So hopefully you got these all. You can see a triangle. It's going to take a 120-degree rotation to map the triangle onto itself. and 72 degrees for the pentagon. Right? Pentagon has 5 sides, and then we did on the last one, octagon has a 45-degree angle in order to map it onto itself. So hopefully y'all got those. Okay, so now let's actually use this with points on our shape. So it tells us the diagonals of the regular hexagon shown form 6 equilateral triangles. Use a diagram to complete the statement. So a clockwise rotation of 60 degrees about P maps R onto what? So what this is saying when it says 60 degrees about P means that we're rotating it around the point P. Okay, so that's what we're rotating around. It's like the center of our clock or Ferris wheel, whatever you want to think. Alright, so we want to see R is going to move to what point if we rotate it 60 degrees. Okay, so what we need to know here is this is a hexagon. It's a regular hexagon. So since it's regular, we can use our little rule of 360 divided by the number of sides. Well, how many sides is it? 1, 2, 3, 4, 5, 6 sides. So 360 divided by 6 gives us 60 degrees. So we know every 60 degrees, every time we rotate it 60 degrees, we should rotate it onto itself. Alright, so where's R going to go if I do a clockwise rotation 60 degrees? Alright, so if I go 60 degrees, okay, R should go to S. Alright, it'll map R onto S if I were to rotate this hexagon 60 degrees. So we're going to put S right there, and I'll do it real quick just so you can see what I'm saying. Maybe I will if it'll let me pick the item. Selecting the entire thing. Well, maybe it won't let me map it onto it. Okay, I thought I could. Oh well. So, but anyways, you get the idea. This point is gonna rotate to that point, and at that time, the shape's gonna be right on top of itself again. So now a counterclockwise rotation of 60 degrees about what is going to map R onto Q. So what will we have to rotate counterclockwise 60 degrees to map R to Q? Well, if we go counterclockwise 60 degrees to get R to Q, then we must be rotating around P again. Okay, so we would put P right here for our answer number 7. Alright, now right here, okay, we're going to do something a little different. We're going to do a clockwise rotation of 120 degrees about Q. So on this one, alright, Q is our center point, not P. Okay, so I'm going to erase this. So now Q is the center that we're rotating around. So it's the middle of our Ferris wheel or our clock, however you want to think about it. Clockwise rotation of 120 degrees about Q maps R. So where's R going to go? So what you want to do is ignore all of this stuff over here. Okay, because we're just going to rotate all this around Q. Okay, everything that's near Q is going to rotate around Q. So if I rotate R clockwise 120 degrees, that means 2 rotations, right? It's going to take 2 turns. The others were just 1 turn because they were only 60 degrees, and every 60 degrees will get us to a new place. So R goes 120 degrees, so it's going to rotate once to here, to P, and then another 60 degrees is going to make it go to W, because we're going clockwise, right, the direction of the clock. So R is going to map onto W if we do a 120 degree rotation about Q. Okay, and the last one, counterclockwise rotation of 180 degrees about P. So we're going back to where P is in the middle. P is our center point, and we're rotating 180 degrees about P from V. Alright, so again, 60 degrees is 1 turn. We're going to go counterclockwise, which is this direction, okay, against the direction of the clock. So 1 turn is 60. A second turn is 60 more, which is 120. And then a third turn is 60 more, which is 180, which is what we want. So we're going to go from V up to the point R. Okay. You say, well, that looks like P. That's because I wrote over a little bit. So we're going to go to the point R if we do 180 degree counterclockwise about P. All right. Let's keep on rolling. Okay, so right here we want to identify the rotation. Name the image of E for 72-degree rotation counterclockwise about X. Scroll down here. You might want to zoom out. Zoom out a little bit. Okay, that's a little bit better. So we're going to name what E goes to for 72-degree rotation. So you see this time we have a pentagon, but it's a regular pentagon, so we can do 360 divided by 5. And we find that every time we go 72 degrees, we're going to have the same pentagon again. So since we're going 72 degrees counterclockwise about X, X is our center, E is right here. So if we go 72 counterclockwise, that means we're going to go this direction, opposite the clock. 72 goes from one point to the next. So we would be taking E and moving it 72 degrees counterclockwise to P. So our answer to that is P. That would be the image that P would be, or E would become, would be P. All right. Okay, so a little bit different here. Name the image of P for a 216-degree rotation clockwise about X. Still have the same pentagon, so we're still doing 72 degrees. Okay, so 72 degrees. Well, how many turns is that for 216? So you can divide it. 216 divided by 72, and I'll tell you we're going to do 3. 3 turns to go 216 degrees. So we're going to be moving P clockwise about X. X is our center. So clockwise is going to be this way. So that's 1 turn, 2 turns to get to N, and then 3 turns will get us to T. So our answer is T. Now this one's a little bit trickier. Name the image of E for a 144-degree rotation about N. Okay, so 144 degrees. Well, how many turns is that? 144 divided by 72 equals 2. So that's 2 turns that we're going to make, all right, from E, and we're rotating it clockwise about N. So N is this point. This is our center now. So everything is going to be moving like this clockwise. Well, clockwise will be this way. So we're going to be going clockwise around N. All right. No wait, sorry, counterclockwise. My fault. I'll underline that so I don't mess up. It's going to be going counterclockwise. So I was right. We're going to be going this way around N. Okay. So starting up here, we've got to go 2 turns rotating around N. So I'm going to go 1 to X, and then a second one to T, which is all we need, 2 turns. So the answer to this one is also T. All right. So I hope that's not real confusing for you, but just visualize that we've got another shape down here where N is the center, and maybe some more triangles around here, and just kind of ignore all this stuff that's up here, because we're just going to rotate around N. The only parts that matter are the parts that are surrounding the point N. None of this stuff's touching N, so it's not important for that particular problem anyways. Okay. All right, let's see, last one. All right, last one here. So it's a little bit different. Name the image of BM. Now BM, remember, is a line segment. Okay, that's not just one point. That's a line from B to M. It's this entire line. So we want to see what is BM going to become. Okay, which line is it going to become if we go 240 degrees counterclockwise about M? So M is our center. We've got a hexagon, so that means since it's 360 degrees for a circle and there's 6 sides, every time we go 60 degrees, we're gonna be mapped to a new place. So how many turns is 240 degrees? So 240 divided by 60 is going to be 4 turns. So I'm going to do 4 turns from BM, the line BM, and it's going to go counterclockwise about M. Counterclockwise would be this direction, right? So we're going to do 4 turns. So from here to here's 1, and then here to here's 2, 3, and 4. So now this line BM is going to be this line, right? DM. So my answer would be DM. Like I'm sliding in her DMs, right? Okay, so that would be my answer for this one, DM. All right, hope you guys enjoyed. Let's go ahead and get some practice going.